Okay, so we will continue from where we left off last time. We were talking about networking. Today we'll talk a little bit about client server systems and remote procedure calls and remote method invocation. Okay, so that's the programming model that we will assume in this class for distributed systems. Towards the end of the class, I'll talk about distributed file systems. Okay, we will have a class on Wednesday. I know that many of you may not be here. It's going to be a shorter than usual class, but I do want to have that class. Otherwise, we will not have a class for a guest, not a guest lecture, but a special topics class. I want to do a special topics on cloud computing next week. And if I skip this Wednesday's class, there won't be any time. There are two more topics, distributed file systems and protection. Each will take a class. If we have a class this week, then I can do a special class. So I decided to go ahead with having the class on Wednesday. If you cannot make it, do go look at the recording after the fact. Okay, and if you can, that would be great. All right, so we'll talk a little bit about client server. So the background to keep in mind is we were talking about networking last time. Okay, so I introduced the protocol stack, the TCP/IP protocol stack. I said TCP/IP is the network protocol used for communication, okay, between an application receiver and application sender. So we'll build it from that point on and start talking a little bit about real applications that are distributed. Okay. The most common way of implementing a distributed application is the client server model. Okay. The other model is referred to as the peer-to-peer model. Okay. In the client server model, there are two types of application components, a client component and a server component. As the name server suggests, it's essentially a process or a collection of processes that provides a service that is willing to accept requests from other entities and process those requests. Okay, there are many types of servers, file servers, database servers, print servers, web servers, okay, so whole class of mail servers and so on. Okay. Servers may themselves be distributed, they don't have to be on a single machine. For large application, servers are typically going to run on more than one machine. Okay. Here we will not look at that scenario, we'll look at a server running on a single machine and then clients running on many machines as well. Okay. The client is the other component of your distributed application. It's essentially a program that uses this service. Okay. You know what clients do. You have mail clients, you may have FTP clients. So basically these are all client-side application processes that are going to communicate with the server. Okay. And the way client-server applications are built. So the thing to keep in mind, the reason this is called server is typically going to be the entity that's providing the service, and the clients are the entities that use that service. Okay. In a peer-to-peer model, which is not something I'm going to talk about here, okay, there is no real distinction. All entities, the application does run on multiple machines, but all entities are roughly equivalent in terms of what they do. Okay, so in a peer-to-peer model, a peer can act both as a client and a server. It can provide a service to other peers and it can request service from other peers. Okay, file sharing examples or BitTorrent are all examples of peer-to-peer model, these applications. Okay, most of the applications in the distributed environments are built based on client-server. Okay. Servers are more distinguished entities that provide the service. Clients consume resources or send requests to servers. Okay, that's basically the model we will assume. Okay, the way client-server applications are built is the client must first set up a network connection with the server. Okay, this may be using TCP/IP or any other protocol that may be used for communication. Okay. To establish a network connection, the client must first find the server. Okay. And there are many mechanisms to locate where the server resides based on its name or some other mechanism. It could be hard-coded, or it could be something that you figure out at runtime. Okay, so for the client to communicate with the server, you must first locate it in the network. You must find as in you must find either an address for it or figure out which machine it's running on. And then once you figure that out, you establish a connection with the server. Okay? Once a connection has been established, then you can send requests to the server to perform some action. Okay? And then the request goes to the server will process that request and send back a response. Okay? This is the way typically a client-server application would work. And it doesn't matter which one. Same would be true whether it's web browsing or anything else. Okay? In web browsing, your client is the browser. Okay? The server is a web server. when you click on a link, well, not click on a link, but if you go to the address bar of the browser and type in a URL, okay, the URL contains a name for the server. That's the www. Let's say umass.edu. That's a human understandable name for the server. Okay. The browser has to then figure out where the server is, okay, because that name doesn't actually tell it anything more than that's the server you want to communicate with. So typically in this case, you would do something called a DNS lookup to translate that name to an IP address. The IP address will basically locate the server, and then the browser will set up a TCP connection with the server. Okay, just to explain it in terms of what we talked about last time. Once the connection has been established, then you send an HTTP request. Okay, that's a request for a web page to the server. Server receives that request for the web page. It will retrieve that web page from the file system. If it's a static web page, if it's something you have to do processing on, it will do some processing and generate that web page on the fly, send back a response. Okay? Same kind of interaction is true. Doesn't matter what kind of client or what kind of server it is. Okay? So that's the thing to keep in mind. Now, with that background, we are going to look at how do you program a client and how do you program a server. Okay? How do you write a client code for a client and code for a server. Okay? One method for doing this is what is referred to as remote procedure call, RPCs, or remote method invocations, RMI. And I'm going to draw a picture to explain how this works. So that's the client machine. That's the server machine. Okay. If you were to write this code, it's from scratch. Let's say you write it in C or something like that, and you are using very basic mechanisms. Then what you would have to do, as I said here, is first you have to essentially locate the server and form a network connection, okay? And then you send a request over the network connection. The request traverses the network, arrives at the server. The server is going to process the request, okay, and then generate a response and send back a response. Okay? And you, the programmer, have to write the code to figure out how to locate the server depending on what application it is. You, the programmer, have to write code to actually form a network connection. Typically, if you've taken 453, you probably know how that works. You create what's called a socket connection. Okay, that's a network endpoint. If you don't know what sockets are, don't worry about it. But you have to write code to do all of that. Okay, and then once the network connection has been established, then you have to actually construct a request. Okay, you construct a message or a request, then you send it off, it is received at the other end to process it. So all of this has to be written in code that you would write for your client and the server. Okay. What we will look at is a programming model that simplifies a lot of this coding for you. Okay. It makes it much easier to write distributed applications. And RMIs or RPCs are one way to do that. And we'll see how to do this in a moment. Okay, anybody here done RMI programming? No? That was supposed to be the last lab, which I then skipped over. We will look at what RMIs and RPCs do. Okay. So the basic idea is as follows. Okay, the server is written, okay, let's say in some language. Maybe it's object oriented, maybe not, doesn't matter. Okay, the server has some procedures or methods, okay, that it basically allows, that implements the service. Okay, so maybe it will say, I'm just making something up. So get web page would be a method that you write in the server. Let's say it's a web server, for example. So typically you expect a request for a page, and then the server will basically call the get web page method, and then it will retrieve the page from the disk and send it back to the server. Now send it back to the client. Okay. Now if you want to simplify the way applications are written, what you want to do is build on abstractions or mechanisms that programmers are already familiar with. Okay. And the way to normally write centralized applications is that you partition them into functions or methods, and then each method calls other methods. Okay, this is how you make your code modular. You don't write your entire code in one giant main method or something like that. You basically have smaller functions, methods. You may have classes or objects, and then you have methods being invoked on objects and so on. Okay? So the idea is, why not extend this abstraction to a distributed environment? Okay, so what we will do now is we will let client applications, okay, call methods. Okay? But the code for the method will not reside in that process, it will reside in some other process. Okay? So you will basically write your application as if you are calling a local method. Okay? Except that the implementation of that method will be in some other process. Okay? That's why it's referred to as a remote method. Okay? The method is not local, it's remote. So in this case, this client, if it wants to request a page, it's simply going to call get web page method with some arguments. Okay? So this is basically, if this was a single centralized application, this code would actually be here, and you would basically go and call that method, it would process the request and so on. But except that now the code for this method resides here. Okay? So all you have done as a programmer is you are simply calling method. But the interesting thing is, you the programmer, do not have to worry about whether these methods are local or remote. Okay? The runtime system is going to figure that out for you. It's going to take care of all of the details of setting up network connections and so on and so forth. Okay? You don't have to do that. Okay? So the runtime system will figure out this is a remote method. It will figure out where is the server that implements this method. It is going to then set up this network connection for you. It will send a request transparently to you, to the server. Okay? Server will execute that method and return a response. So when the response comes back, it just looks like you called a local method and the local method returned a response. Okay. So now writing distributed application looks no different from writing your normal application. So you can write the application in Java. You can just call a method on an object, except that that object is remote and the implementation of that method is remote, sitting on some other machine. But you, the programmer, don't have to worry about these details. Okay? You just tell the JVM that this is a remote method, and it takes care of a lot of the details of, hey, I need to set up a network connection. I need to send a message saying execute this method with these arguments and then get back a response and hand it back. And all of those details are handled by the runtime system. Okay? So you have made writing distributed applications as convenient as writing normal applications where all of the code is actually in one process. Okay? So this is a nice abstraction that allows you to write distributed code, and we'll see examples of how to do it. Okay? So this is the basic idea behind a remote procedure call. In the Java world, it's called remote method invocation, or RMI. Okay? The generic term is remote procedure call. As the name suggests, the procedure or the function you're calling is remote, and you're making a call which will basically be sent over a network in order to execute. And the way this typically works, this is the basic idea beyond what I just described here. The server here is going to export a set of procedures. Okay? And it's going to say these are methods that some other client can invoke on this code. And not every method is something you can invoke remotely. Okay? You have to declare that these are the set of methods that I allow some other application on other machine to invoke on this server. Okay? So then once you've basically exported those procedures to use the server, the client is simply going to invoke one of those methods, and the OS and the runtime system will manage the communication for you. Exactly what I just said. Okay. Now there are many details one has to worry about in order to implement such a system. Okay. And you can imagine that a lot of the hard work is being done underneath by the runtime system for you. Okay. All of the details of how do you establish a connection with the server, how are you going to send this message, if the procedure has arguments, how are those arguments sent over, how are they unpacked at the other end, and so on and so forth. Okay, so the way this is done is basically through what are called stub codes. Okay, this is automatically generated code that you will basically include as part of your application. You don't have to write this code. Once you declare that the methods are remote or invoke a remote method, there's extra code that's going to be generated for you. Okay, if this is written in C or C++, this code has to be linked with your application, and that's going to do all of the extra work of setting up the connection. Okay, in Java, that code is handled by the runtime system for you. Okay, that basically you just link it to the right methods, and then it's going to take care of all of the details. Okay? So this code is referred to as stub code. Okay? This is basically code that is auto-generated, that's going to do all of the work for you. So when you basically call this method, you will have an implementation of that, not an implementation, but there will be basically, it will go into the stub code, which is like a library that will take that method and do all of the extra work of setting up network connections and all of it. And the server side as well, there is some stub code. So there is basically, there's a client stub and there is a server stub. Okay. So this comes here, then this basically the stub code is talking to the stub code at the server. You send off a message, and the stub code here is going to invoke the actual method that was invoked by the client. Okay, that method will execute at the server. A result will be generated. It will come back to the stub. The stub will send it back here, and then this will hand it back to the method that was invoked. Okay. So all of this stub code has to be generated by the runtime system. Okay, so you basically have to deal with lot of the underlying details, such as backpacking the message, unpacking the message, and so on. But the important thing to keep in mind is when you write client-server applications, typically you do not make any assumptions that the client machine and the server machine run the same OS, run the same platform. None of that is assumed. Okay? You can have C code running on a Linux box calling a server that's running on Windows. Different application, rather different OS platform. You don't even have the hardware architecture to be the same. Okay? This could be 32-bit machine, that could be 64-bit machine. This could be Intel machine, that could be, let's say, a Spac machine. Okay? So you don't even assume that the client and the server machines are heterogeneous. Okay? So when you basically a browser talks to a web server, nowhere is it assumed that the web server is running the same OS as you are running. You may be running Mac, web server may be running Linux. Yeah, the same idea is true even here. Yeah, so this heterogeneity brings additional complication, because if you start sending arguments, the arguments have to be interpreted accordingly depending on what the other end is. So very simple things like the client machine may be using big Indian and the server machine may be using little Indian. I assume you know what big Indian, little Indian is, right? Okay. So even integers are read differently on whether the client is big Indian or little Indian. So if you just send some bits over, okay, and you just read those bits without understanding what the client or server was talking, you will basically get garbage if you are not the same architecture. Okay. So the stub has to deal with all of these details. Okay. How do you do the translation? So in other words, all the arguments, all the messages have to be translated so that regardless of the end platform, it still makes sense. The good part is you, the programmer, don't have to worry about it. If you are actually writing all of this code without using RPCs, you would have to worry about it. Some bits come over a network, you have to interpret it accordingly. Okay? Now you are programming at a much higher level of abstraction, so none of this is something you worry about anymore. Okay? So here is basically the skeleton of what the client and the server does. The server, once you write it, is going to basically sit in a loop. Okay? So in this loop, it's going to wait for a command or a request to arrive on a network. Once the command arrives, it's going to unpack the parameters, okay, call a procedure. Okay, so this is multi-threaded typically. So it'll call it, it's give this request to a thread and say go execute this method. Okay, the thread will then call this method here, okay, and then send back a reply. And then you sit in a loop because you may have multiple clients communicating. You will have a loop that is just accepting requests, processing them, sending a response. Your client basically looks like this. You build a message, you send the message, you wait for the response, you unpack the reply, and you return. Okay? So while the method is being processed, you're just going to wait for the reply to arrive over the network. Yeah, I'm going to show some Java code in just a little bit. Okay? But before we do that, we have to deal with a few details here. Okay? First question is, how does the client machine know, okay, where the server is running, what machine it's running on? Okay? And this problem is basically referred to as the problem of binding. Okay? Binding basically says locating and communicating with the server. That's what binding is referred to. And there are two ways to do this typically. One is you hard code it in your client code. Okay? When you basically invoke the method, you tell the stub saying the server is running on this machine, and the stub simply goes and communicates with the server on that machine. Okay? So in this case, at compile time, you need to know where the server is running, and you basically are not even compile time, but when you write your code, you need to know that the server runs on that machine. and you hard code the address of that machine, and then the client will only communicate with that. So this is very straightforward, but it's not at all flexible. If the server now runs on another machine, you have to rewrite your code, okay? Change the hard-coded address, recompile it or something like that. Okay? In most cases, what we do is binding is dynamic. Yeah, you use what is referred to as a name server. Anybody heard of a name server? Yeah, name server is essentially a directory service that maintains a table. So what happens is when the server starts up, it registers itself with the name server. It says, I am a web server. Okay? I'm providing the service, and these are all the methods that I have exported, and I'm willing to accept requests on those methods. Okay? So you register yourself with the name server. And then when the client starts up, and if it wants to find the web server, it says, where is the server with this name running that exports this method? Okay? And then the name server, which is an intermediary rather. Okay, so there's a name server. Okay. The server is going to register itself. Okay. And the client is going to do a lookup. Okay. This is like looking up a telephone directory. Okay. You may know the name of the person you want to call, but you don't know their phone number. Okay. They are registered in the phone directory. You just go look at the phone directory and you find their phone number. Same thing is true here. Okay. Server registers itself with a name server. It's called a directory service also. And then the client is going to do a lookup saying where is the server with that name running, what machine is it running on, and then the name server will say it's running on this IP address and it's listening on this port number. And then once you figure that out, then you basically can set up a connection. Okay. So that's an important aspect of writing any distributed application. The clients need to know where the server is located. In RPC systems, you use a name service. In the internet, you use what's called DNS, domain name service, same principle. Okay? This is how you will translate www.umass.edu to an IP address. Okay? When you type that into your browser does not actually know what machine the web server is running on. It's going to do a name service lookup. Same principle applies in any client server application. Okay? So the most common way to find your server is to register the server with the name service and do a lookup. So this dynamic name service is going to be, dynamic binding is going to be done at runtime by the stub code. Again, the nice thing is you don't have to worry about too much details. You can just specify the name of the server, and then the stub code will take care of talking to the name service and so on. Okay, is that clear? Okay, how to find server. Okay, so now we'll talk a little bit about how all of this is done in Java. Okay, so Java provides you a remote method functionality out of the box. You can essentially take a method that you have written, turn that into server, and allow other clients, other Java code running on other machine to start invoking those methods. Okay? So there is a naming class. This is basically the name service that the JVM is going to support. So you can basically, there are two methods here. Okay? Bind registers the server with the naming service, and lookup is going to look it up. Okay? Basically, there are two things. There's a registration part and there's a lookup part. So if you use the naming class, you can use either of those to do whatever you're doing, depending on whether you're the server or the client. I'm going to show you some code in just a moment. Okay? And then basically the way you are going to actually invoke methods, you use something called a unicast remote object. Okay? This is basically going to allow you to invoke methods or call methods which underneath is going to use TCP for you. Okay? Now you don't need to worry about what TCP does or anything like that. You just say this class basically is of this type, okay, and then any methods of the class you will be able to invoke remotely. And just some extra details, RMI registry is the name of the process, that's the server side name server. When you do a bind or a lookup, that goes to this process that's also running on the machine. Okay, so let me show you some code here. Okay, so we are going to go step through a very simple client server code. Okay, the server is going to essentially have one method which is an hello world method. You call the method is going to return a hello world string for you. Yeah, so you can implement any service, but this is a trivial one. Okay. So what the server has to do are two things. It has to basically specify the interface, which is the list of methods it's exporting for any client to invoke. And that's the interface part. And then there's the implementation part, which is an implementation of all of those methods. Okay, the server has two parts, the implementation of methods and the interface of the method. This is the interface code. Basically, it says this is the hello class. It extends our Java RMI remote. That's basically the RMI classes. Okay, and says there is only one method that I implement as a server, which is the say hello method. Okay, so that's basically, this is the method that any client code can invoke. Okay, so if you, the client code, you say hello, that method is going to come to this code running on the server and execute that method. Okay, you have to deal with exceptions and so on, which I'm not going to worry about here. This is the implementation of the server. Okay, that was the interface. This is the implementation. Okay, so basically you say this is the implementation of hello. Okay, and as I said, you basically have to extend this unicast remote object, and that's basically the functions that allow you to implement RMIs in Java. Okay, it doesn't do much. This is the method that we just declared, is a remote method. Okay, so say hello. All it's doing here is essentially returning a string. Typically, what would happen is this would be a request that has been sent. It would have some arguments. So if you were doing get web page, so this would be get web page. It would have an argument, which is the address of the page. Here you would go retrieve the page from disk and then basically construct a response and return the response. Okay. In this case, all we are doing is the client is going to call this say hello method. We are just going to return a hello world string back. Okay. All right, so that's the implementation of the method on the server. Okay, this is the main function on the server. Okay, nothing much to do other than to declare a new object, which is the hello class. Okay, and then once you do that, the object is ready to receive a request. And the other thing you do is you register yourself with the name service. Saying I'm a server. When you start up, you say I'm a server, and I'm going to be basically listening on this address. So if any client requests the service with that name, point them to me. Yeah, and then you register the object as well. As you can see, the object is also registered with the name service. Okay, so fairly straightforward. Any questions here? Look at the client code in just a moment. Okay, yes.
So it's like MyHost, like the domain name or something?
Yes, so here you can basically, this is, you can use any name, any method you want. Here, basically we say this is the domain name and that's the, so this is like URL like scheme just to mimic what's happening in the web. Okay, but you can basically use any string. You can say I am server XYZ, and then if you're, it has to be unique, of course. Okay, then if, and so here we basically just decided to go with the name of the host, which is your domain name and the name of the server. But that's not a requirement. As you can see, that's simply a string. So you basically provide a unique string that is your name. Okay? The name here happens to be constructed using the domain name. Yes?
So this is like live and deployed. How would you like avoid conflicts? Because like if you can just make a name.
Yes. So how do you avoid conflict? So basically, that's something you have to deal with. This is the same problem of if you had DNS. Right? How do you avoid conflict? The first one that grabs the name gets it, right? So if you have a .com domain, you can say no two independent entities can have the same domain name. The first one that grabbed it got it. The other one has to pick something else.
So
okay.
Yeah,
if you bind, if you start another server, it starts using the same name, you can't register it. The name service will say this name, there's a server already with this name, pick something else. Okay, so you have to find a way to make it. So the assumption is that on a given machine, all the server code that is basically being written is under the same administrative control. So somebody is going to figure out that they have different names, for instance. Okay. Typically what will happen is this will be I'm a print server or I'm a file server kind of thing. So they'll be doing completely different things. So the collision, chances of collisions are rare, but yes, if you're 10 of you are writing lab 3 and you're going to give the name of the server is lab 3, the first one that registers lab 3 is going to get it. Other people will have to find other name for their server. They can't call their server lab 3. Something like that. Okay. Any other questions here? Okay, so here is your client, which is also fairly straightforward. So what we are going to do here, this is some extra code that we don't really need to worry about, is going to take the string and display it on the screen. Okay, so there's some extra code to do all of that, so which is why we have a hello applet. Okay, so first thing you're going to do is do a lookup. Okay, so a lot of the other code you can ignore. So here you're basically going to say, I'm going to look for the server. Okay. Now this code has been written under the assumption that the client and the server are independent processes, but they're still running on the same machine. Typically, that will not be the case. Okay. So in that case, you will have to specify the name of the server somehow. But here, you're simply getting the name of the host and appending the string to it. And that's because it assumes that you are running the code on your laptop, for instance. Yeah, but nevertheless, you look up the name of the server and from the registry. Okay. And once you're done that, the only thing you're going to do is say object that say hello. Okay, so you'll see, so that's basically all you have to do in order to invoke a remote method. Okay, the code looks exactly like you are invoking this method and the method was local. Okay, you didn't do any fancy networking stuff, none of that. Okay, that's done underneath for you. So you wrote the code assuming you're just writing local code. You're looking at that code there, I mean just that statement, you couldn't tell that the method was remote at all. It just say looks like you have an object and you called a method on the object. Okay. But underneath, as I said, what will happen is that say hello method will go to the stub. Okay. You already found out where the server is. The stub will bind to the server. It will actually internally create a TCP connection. Okay, it will set up a TCP connection. It will, if there are arguments to that method, you would construct a message with those arguments here. You would just construct a message saying client wants to invoke method say hello. That's what essentially your message is going to say. You'll send that, the stub will send that over here. Okay, the server stub will say, here's a request for a method. Client is requesting execution of method say hello. Okay, it will then go to the server code where you implemented this method. Okay, you will basically execute this method, this code on the server, which is going to simply return a string. The string will be, you'll construct another message using the string in the stub code. Okay. Stub will send it back. All of those things will happen when you call this say hello method underneath. Nice thing is you have to not deal with any of those details. If you are writing C code using plain socket, you would actually have to write extra code to do everything I just said. Yeah, so you are essentially few lines of code may become few hundred lines of code if you did not use things like RPCs of RMS. You will be programming at a much lower level. Here, writing distributed application looks as straightforward as writing normal Java application, except for the details of registering with a server, name service, and so on. So long as you deal with those details, everything else looks the same. Any questions here? Okay, so this we will assume is the programming model for writing client-server application as far as this course is concerned. There are many other ways to do that, of course. But RPCs and RMIs are a very nice way by which you don't deal with a lot of the internal details of communication and so on. Okay, so as you can see, once you call the method, you also display a string that the method has invoked. That's the client code, but that's just some extra things you written just to show what came back from the server. Okay, typically, if you are requesting, let's say in this case, if you requested a web page, then you would get the web page and then you do all the rendering to display. Similar stuff has to happen. So you have support for remote methods or RPCs in many different languages. Okay, Java supports it out of the box. In C or C++, you have something called RPC, so you have to use some extra libraries. Okay, it's not part of the language, but you use some extra libraries to deal with these issues. Okay. So I think that is all I have for RPCs. We'll talk about file systems next. Yeah, are there any questions here? Okay, so we talked a little bit about the programming model. Okay, we started with networking. We talked about how to write programs using client-server model. Now we will look at a particular distributed application, which is a distributed file system. And so we are building one level up. So let's look at a real application that's been programmed using similar method and see how it works. Interesting thing as an anecdote is RPCs. Okay, they were designed, I think, back in the 70s or 80s. Okay. They were originally designed for this application. Okay. Sun Microsystem in those days were writing a distributed file system called Network File System, NFS, which is still very popular today. When writing NFS, they decided that let's actually have the client and the server communicate using remote methods. In that case, remote procedures actually, because it was written in C. Okay. So the first real commercial implementation of RPCs was for writing a distributed file system. Subsequently, they figured this idea is actually general, the notion of invoking remote procedures. So they basically made it its own tool and said, no, anybody can write any code you want using this notion of RPCs. But the very first implementation of RPCs was for implementing NFS, which was a file system that was written many decades ago and is still in use. And that's just as an aside, but let's talk a little bit about distributed file systems. Okay, so what is a distributed file system? So you probably know what a file system is. We studied that in class. So what a distributed file system allows you to do is access a file that's stored on a different machine, not on your local disk. Okay. Typically, when you access a file, that file is actually stored on your local disk. Okay. What distributed file systems do is they generalize this concept. They allow a client to access a file that's stored on a server somewhere else. Okay. And the access, depending on the file system, may be as seamless as just accessing a local file, except that underneath the file just happens to be on a different machine. Right. So the basic idea is, given a set of disks that are attached to servers, can we share these disks across machines? Okay. Can we share the data on files stored on the disk on other machines, so other machines can also access those files? Okay. So this enables resource sharing. Okay. What you're sharing is disk space. Okay. Now your disks are no longer local, they can be remote, and you can access data stored on other disks. Okay. You probably used some form of distributed file systems already. Okay. EdLab is basically based on this concept. Okay. When you log in to any machine on the EdLab, your home directory, okay, whatever your files are actually not on that workstation. They're stored on some server somewhere else. Okay. But yet you are able to access those files on that machine. And the reason for that is you're using a distributed file system underneath. Okay. Many different forms of distributed file systems out there. On Windows, you have Samba. Okay. In Unix world, you have NFS. Okay. In the Mac, you basically can construct Apple file shares, AFP, AppleShare. Okay. So there are different file systems, and there are many others. We'll talk about a few others here. Okay. So is the idea of what a distributed file system clear? Okay, so there are many issues you have to think about when you implement a distributed file system. Okay, the concept that we look at here are not just what it is, but how you implement it underneath. Okay, and there are 4 or 5 different things we look at. The first is naming and transparency. We'll look at remote file access. We'll talk about caching, and I don't know whether we'll have enough time to talk about the last 2 today, in which case we'll come back next time and discuss those. Let's start with naming. So what does naming mean? Okay, so basically it's the problem of how do you access a file stored on some other machine? What name are you going to use? What naming scheme are you going to use to access those files? Okay. And at a very high level, there are 2 important concepts to keep in mind. One is referred to location transparency. The other one is called location independence. Okay. Location transparency says the name of the file does not reveal its physical location. And if you're not location transparent, then you do reveal the physical location. And there are, the best way to understand this is to 2 examples. So I'm going to use okay, let's take the example of the web. The web uses a naming scheme. So here is a name for a file. That's a URL. That's the name of the file, index.html, that's stored on the UMass web server. Okay. Now the question is, does this name reveal the location of that file or not? Is it location transparent or is not location transparent? Yes.
What do you mean by physical storage location? Like, is it the block on the disk or the directory it's on, or the server it's on?
Let's
like
just say it's the
website?
server for now.
Okay.
Yes.
It's transparent. The UMass server could or may not fetch that web page from somewhere else. Like call to another server to get the page and then return it to you.
Okay. So I'll just hold off on that and what were you saying? Okay. So let me give you another example and then you can tell me. So I'm going to give you this is the naming scheme, sort of the naming scheme used in the EdLab. Okay? That's the name of a file. Okay? The directory is not on your local machine, it's somewhere else. So the question is, does this name tell you where the file is stored? Does it embed any information about the server on which the file is stored? The naming scheme. Yes.
Those directories, so I guess not necessarily the server, but what directories in the server?
Yes. No, my question is just looking at this name, could you basically tell whether the file is actually stored on a certain server? No, right? I mean, you're just saying home share. This looks like a local file system. It doesn't actually tell you whether the file is remote or local. Okay. Does this name have the name of a server embedded in it? Okay, it does. Yeah, so if you specify this name, whatever client is actually using this name knows that you are looking at this server and a file, that file stored on that server. But if I give you this name and say go get that file, the name of the server is not embedded in the name. It's actually transparent. So this should just tell you these are two different naming schemes. The web naming scheme, the URL naming scheme has the server names embedded in it. The other one does not. Let me give you a second example. If you go to Windows, okay, for example, so you could basically have something like this is a typical naming scheme used in Windows. You say backslash, backslash, you give the name of a server. Okay, that's the Windows server. You basically have a network share and then you specify a file name. Now you can ask the question, does this name of this file reveal the name of the server? Is it embedded in it? Okay, you will say yes. Because so this is not a location transparent name. To access that file using this naming convention, you have to specify the name of the server. To access this file, which may also be remote, okay, the name of the server is hidden. It's not transparent. It's transparent to you. Okay? So these are two different naming schemes. Okay? One is location transparent. The other is not location transparent. Okay? Now, for a file system, you can pick different schemes. Okay? The question is, do you want users to remember what server the files are on and specify that every time? Right? Or do you want to just hide that and provide more easy to use convention? Okay, this is easy. You say home, which is where all home directories are stored. This is my username. That's a file in my home directory. I don't need to worry about is my directory on EdLab server 1 or EdLab server 3. Doesn't matter. Yeah, all I know is it's in my home directory. Yeah, that's an easier to understand name. Okay. In this case, you actually specify the name of the server, the network share, etc., etc. So this is a design decision one makes when you design your distributed file system. Are you going to be location transparent? What naming scheme do you use? Do you want to keep it transparent or not? There are pros and cons. Okay, the simpler thing is to keep it transparent. Okay. Location independence is a different concept. Location independence basically says the name of the file need not change if the storage location changes. Okay. If you actually change this location of where the file is stored, the name that you use to access it does not have to change. Okay, the handle, the name of the file is independent of where actually it is stored. It's a little harder to explain because there are not that many location independent schemes. Most of them will actually change. There's like a URL. If you move this into a subdirectory, okay, then you basically will have to have a different URL, which will say directory index.html. Right? So name has changed. If you move this file into another location on your home directory, his name will also change correspondingly. So they are not necessarily location independent. But there are storage systems where you have a handle. Okay, the handle will not change even if underneath there's a mapping that goes from the handle to the object of the file, and the name doesn't change even if you change it, you change the server or change the directory and so on. So that's what is said here. Most naming schemes do not have location independence, but most have location transparency. Most, not all. I gave you examples of schemes that are not location transparent. Okay, so here are some examples of naming schemes. So what I showed here, this is referred to as an absolute name. Yeah, absolute name essentially has the name of the machine name followed by a path name on that machine. Exactly what happens, the best way to understand is URLs is an absolute name. It has a name of a server and a path name on that server. A Windows naming scheme, same thing. Okay, so you can also do Apple file share and so on and so forth, which use the same thing. Okay, the advantage of using absolute names, which are neither location transparent nor location independent, but they do have advantages, is that you don't have to do, once the user specifies the name, the system doesn't have to do much. It knows exactly what machine, what directory, and what path name of that machine to use in order to access the file. Okay. There is no global state that you have to maintain. We'll see what that means in just a moment. It scales much easily. Disadvantage is now the user has to keep all of that information in mind. When you open a file or when you access a file, you have to specify an absolute name which includes all of those details. Okay, and basically file location, if file is location dependent, it's harder to move. Sharing is harder. And last but not least, this is not fault tolerant because you are specifying the name of a server. Server goes down, directory becomes inaccessible. Okay. If your location transparent names like this, you can keep multiple copies of the file. If one server goes down, you can simply transparently look for another server. Since here you specify the name of a server, you can't just simply go fetch that file from some other server. You have to go to the server that the user specified. Okay, so absolute names have some advantages but also disadvantages. So this scheme that I mentioned here, okay, is actually used in the Unix world, okay, using file systems like NFS. And the way this works is there is a mapping that is constructed at boot time. When you boot your system, okay, there are internal mappings that are set up that basically allow you to figure out what directories are in stored on which servers. And then from that point on, the names of the machines are not specified in the path name. Okay, so example is basically here. So that's not the example. The process is specified there. So when you boot up there, you basically look at a configuration file like /etc/file tab, which is going to basically have a mapping of this sort. You'll say a remote path name, machine name, and a local name. So you might have something like lab server. Okay. You say export home directory. So this is basically on the EdLab server, the directory that holds everybody's home directory. So say that's basically the directory that you're going to map to /home on your local machine when you boot up. Okay. So this mapping is constructed by reading that /fc tab, and it's basically sort of remembered by the file system. So what happens is you have a path name, so you have /user /bin. You have /home. These are all local files on your machine if you construct that mapping. But this is a remote file, or actually a remote directory. Yeah, because this is going to be mapped to that. Okay. So it looks like you are basically have some local directories, because if you are just going to go and say cd/home /on this machine, what is actually going to happen is you are going to descend down this path, and any files in this part of the subtree are actually stored on that server. So from this point on, when you're actually accessing any files, all of those requests have to be handled by this server. So if you go do that and do ls, there's a list files there. That ls command cannot be executed locally, because the files on that in that directory are not even local. They have to be sent off here, to the remote server. You have to get the listing of all the files and display them. So all of that is handled, of course, internally and so on. But the important point is there is a mapping which includes the name of the server and the directory. But that's hidden from the user, because you just take that path name and map it to some local name. In this case, the local name is /home, and then from that point on, the user doesn't have to specify every time that that's the server they care about. Okay, that's already taken into account. So you just simply have names that are location transparent. Don't have to worry about it. Okay, so you have increased the convenience for the user. So you don't have to specify. Like this case, every time you do a CD, you might have to say / /adlab server something. You don't do that. Okay? You basically just specify this mapping. The system administrator specifies this mapping, and then it's done at that point. You don't need to worry about it anymore. Okay, is that clear? Two different philosophies on how to construct file names for remote files. Okay, you don't have to ever worry about these issues when you're talking about just a local file system. Okay, but with a remote file system, there's a machine on which the files are stored. So the question is, does the user have to specify that machine name every time they access a file, or is it transparent to the user? And it's an important design decision. Okay. Advantages of doing this are clearly it's location transparent, as I just mentioned. The remote name can change across reboots. Okay, so on a remote machine, if you move this to export to /home, there you go and change the configuration file. When you reboot, and the mapping to /home is now a different directory where you moved the home directories, for instance, if it was moved it to a different disk or whatever. Okay, so across reboots, you can even change the remote name, okay, and then it will still work. Okay. Now the important thing is this is harder to have the same name across different machines. Okay. It is something that system administrators have to impose, but this flexibility can be used in different ways. So on one machine, okay, you can say this server's directory is mapped down to /home. On a second machine, you might basically say, I map it to /divs. Okay. On that machine, the same directory will essentially become /divs/shenol, because you constructed a different mapping. Right? So essentially, it's harder to have a single unified strategy because the mapping that you use is local to that machine. The system administrator decides where a remote volume, how it is mapped to local on a local file system. Okay, and you can make whatever decisions you want. Okay, so you don't need to have the same name. This can cause confusion for users. On one workstation, if your home directories are here, on another AppleShare workstation, if you put it there, then when you log in there, you need to figure out what mapping is actually used in order to get to your home directory. If you have absolute names, that's not a problem, because there's always one name you're going to use. That's the absolute name to get to your directory. Okay, so this is simply a list of some of the contents of the FS tab on the AppleShare server. As you will see, so this is basically the mapping. So it says /courses/CS300, that's AppleShare server 3. Okay, so this directory is actually on that server. And on a local machine, it's mapped to /courses/CS300. And inside CS300, you have 377 directory, which presumably most of you don't use anymore, but that's essentially how these mappings are constructed. These are all the home directories, these are course directories. This is basically the contents of FS tab. So when the machine, the workstation boots up, it is going to take this server, that directory, and map it to that name on that machine. So when you cd here into this directory, you are actually looking at these files that are stored on some other server. Any questions here? Assume you have at least used a network drive or network share of some sort, that this is not totally out of the blue. Okay, so but different file systems make different decisions. Okay, this is what Linux and NFS do for you. And this is simply a picture of how the directories are mapped, which I already drew, so I'm going to skip this. Okay, and tell you a little bit about some other file systems, okay, which have made other design decisions. There's one called the Andrew file system, okay, which is started as a research project at CMU. Eventually, it became a commercial product that's still sold by some companies, and now some port of it is actually available also in the Linux source tree. Okay. But the important part is not where the file system came from, but what design decisions they made. Okay. In the Andrew file system, the naming scheme is like the web. Okay. First of all, you don't need to construct any of these pre-configured files. Okay. Any Andrew file system, any server can talk to any other server anywhere in the world. And the way you are going to simply basically talk to another server is you say /AFS, you can say file server.cs. Okay, so you say /AFS, then you specify the name of the server that you want to talk to. Okay, you can simply cd into any server and then you specify a path name on that server. Exactly like what you do for a URL, where you might have www.csumass.edu. So if you do this, you can basically go into any directory of any Andrew file server in the world, provided the user has made your directory world readable, of course. Okay, so otherwise, you can go and access any data that anybody has done. So you can essentially, without constructing any mapping, you basically specify full path names, absolute path names, but the mapping is constructed on the fly. When you cd there, you'll essentially go to that server into that directory. Okay? So it uses the same naming scheme. It's called a global naming scheme. So you basically have the same name for a directory and a file, regardless of what machine you access it on. And the naming scheme says you always start with /AFS for Andrew file system, specify the name of the server, okay, and a directory on that server. Yes, you have a question. Okay, so that's the structure you use. Okay, it's global and it's absolute. So there is always the same name. You will not have this scenario where on one machine you map the home directories to some directory and on another machine another directory. That kind of stuff doesn't happen. You will basically use the same name. Okay, just exactly what you do for the web. You have one URL, regardless of where you access that your web page from, you use that URL. Okay, so advantages of global namespace is naming is consistent. Is the biggest advantage. Okay, you use the same name regardless of where you come from. Okay? Disadvantages are there may be some limited loss of flexibility because you have to use the same name. The name is long, you can't construct shorter aliases and so on and so forth. There is caching issues, which I'll come to in just a moment. There are performance problems to scale a global namespace, always, because you will need to do this, you will need a name service, which will be basically global also because the file system's namespace is global. Having a global namespace and a global naming service will bring its performance issue. You have to scale to that level. Okay. In NFS, you don't have to do all of that. Your file system may be fairly local. In the Ed Lab, your one server, 20 workstation. That's all that you need to deal with. 20 on the order of 20 machines, not hundreds of thousands of machines. Okay, so now about 15 minutes left. I'm going to talk. So that's all I have to say about naming. The next thing I'm going to talk about is the actual method by which you implement a distributed file system, as well as caching issues that come into play to improve performance. Okay, so typically any file system, any distributed file system is going to use one of two methods. One is referred to as the remote access method, or remote service method. The other is essentially called what is referred to as the upload download of the caching model. And I'll give you an example to show what this means. So this is your server. as file foo. So it is an application here that wants to access file foo stored on a remote server over a distributed file system. Okay, the distributed file system can be implemented one of two ways. Whenever the application issues read or write request on that file, you treat this read or write request as RPC requests, and you essentially send them as read or write request to the server. Okay? So the server is basically then going to execute the read write RPC request and send back responses. Okay? This is referred to as the remote service model, where every request that is being issued by the application to a remote file essentially becomes a remote procedure call that is sent to the server. The server executes that request and then sends back a response. Okay, so all requests are essentially forwarded to the server. That's one model. Okay. The other model for implementing a distributed file system, this is the remote access model. The other model is what is referred to as the caching oriented or the upload download model. So when you open a remote file, you say that okay, that file is remote, what will happen is then the OS here is going to go to the server and fetch a copy of the file and cache it locally. Okay, so you make a copy of the file that's stored on the server, and there's now a second copy of the file that's stored on the server. Once you have made a copy, all subsequent reads and writes are actually going to be sent to the local copy. You're going to only make changes or read the local copy. And if you make modifications, periodically the modified version of the file will be sent back to the server, so the server also has an up-to-date version of the file. Okay, so this is referred to as the caching oriented model, where whenever you open a file, you bring the entire file over and subsequent IOs are local. In the remote access, all IOs are always remote. You always send them off to the server. The server performs all of the IO operations on one master copy. Okay? So these are two ways to implement a distributed file system at a very high level. Okay? Remote service or caching oriented. Okay, so let's ask what are the pros and cons of this. Let's start with remote access. What might be some advantages or disadvantages? Okay, yes.
Heavy workload for the server, light workload for the client.
If workload on the server is heavy, yes. Okay. So two different points. One is that all requests are sent to the server. So the load on the server is the sum of the load of each client. Remember that this is not the only client that will be accessing that server. There will be many client machines that are all accessing files. And they may be accessing different files, but still all requests are to be sent to the server. So the load on the server is going to be high. Okay? That's one. The second point that was made was basically with regards to what is referred to as consistency. Because if you make local changes here in the other model and this machine crashes for any reason, before the changes were sent over to the server, then the changes will be lost. Okay, OS can crash, people can shut down the machine without just having the code or whatever, okay, and then there's a risk of losing changes. If all write requests are actually sent to the server, the changes are always made on the master copy, so the master copy is always up to date. Okay. And these are fundamentally the trade-offs. Okay. The trade-offs are essentially, the first trade-off was a performance trade-off. The second trade-off was essentially a reliability or a consistency trade-off. So you will realize that in the caching model, performance is going to be better. All IOs are, once you bring the file over, all IOs are local. Okay? Local writes clearly are faster than remote writes. Okay? So in a remote write, you have to pay for the latency of a network message plus a disk IO. Okay? A write request, the latency of a write request is the time to send the message over a network plus the time to perform the operation on the remote machine. So that's going to be clearly slower than if you are just doing a local write here. So the initial part of fetching the file may be somewhat slow depending on the size of the file, but once you bring the file over and it's cached, all IOs are going to be local. So this will have better performance. The caching oriented will have better performance, and the other one will have worse performance because it's slower. Moreover, the load on the server is higher because there are many clients sending the code. So it comes down to fundamentally a performance versus consistency issue. Okay. Although the caching oriented model has better performance, as we just said, there's a consistency problem there. Okay, and the consistency problem is not even the problem when the machine crashes. Let's say there are two, so file, let's say client 1 opens file foo, okay, and the file is brought over here, and it starts making some changes to the file. Okay. Now here is client 2. It also opens file foo, okay, and this copy is now brought over here. First of all, this copy may be outdated. Okay, the cached copy here may be newer. You have made changes that have not yet been sent here. Okay. So when client 2 opens that file, okay, it will actually get an old version of the file. Okay, so you may see old or stale data in your file system, which is even worse the problem than just losing write. Okay, you think about this. So if you and your lab partner are working together. Okay, so you say I will change some code. I'll write to this whatever lab1.java or some such thing, and I save, and all of that changes are just made local. The changes haven't yet been sent, and your lab partner just opens that file from the server, and they still see the old code. They will say, I thought you just made some modification. I'm not seeing it. Okay, these kinds of problems can and do occur. Depends on how the file system implements it. Changes can be up to 30 seconds. They may take up to 30 seconds to propagate through the system in some real implementations of these file systems. Okay, that's a caching policy used. Okay, so you may have consistency issues. Performance is better. Consistency may be worse. Okay. In the remote access model, since there's only one master copy, this problem doesn't occur. You make changes, you send them to the server. Somebody else opens the file, they always get the most recent version. You will never get stale data. But in a distributed file system with users caching, you may have the problem where you get stale data. Yes.
So with like a centralized version, if you have two people open the file at the same time and they're both doing like writes concurrently to it,
yeah,
like how does it resolve those? Does it just like corrupt the data?
Right. So this is a good question. Right. So I'm going to draw a picture here. Okay. So in the remote access where there's a centralized version, let's say two clients have both opened file foo and they're both writing to this file. Okay, the question is what happens? Okay, so now if you have to realize that if there are two applications writing to a shared file, this becomes a shared data structure. So technically, you should have been using some locks. Okay? File system may or may not support locking. Okay, if you don't do any locks, you simply start writing, then you may have basically writes just trampling on one another. Okay, and you may have corruption. And this is not an uncommon case. The example that was just mentioned actually happens in mail servers. Okay? That's your inbox. Right, so this is your inbox. This could be the incoming mail server. New mail arrives, you basically go and write to your inbox. And this is basically your laptop where you have your mail application that's reading or writing. So that's fine. So if you don't use locks on your inbox and new mail comes and you deleted one mail from your inbox and both the inbox tries to be updated, you will have corruption. Okay. So this is no different from using threads and data structure. If you have files that are being read or written to at the same time by multiple applications, you have to use synchronization for correctness. The file system will merely accept whatever read or write command you send it. Well, it's not the file system's problem that multiple applications are accessing the file at the same time. At a higher level, you better have put in some synchronization. That's the real answer. The file system may or may not even support locking. Some file systems do, in which case you are better off basically grabbing a write lock before you issue a write, then release it and so on. And others don't, in which case locking has to be implemented in libraries. But nevertheless, file system won't prevent you from writing to the file at the same time. It will just take the write request and basically put any write into the file. Yeah, but that's a good point to keep in mind. When you have distributed file systems, applications may read or write the same file at the same time, in which case you should be using some synchronization. Otherwise, you will see some problems. All right, so one last point here. I already mentioned what happens with the remote file and caching, so let's just skip this. Actually, let me just talk about this and stop because we're out of time. So, with respect to caching, in the caching model, you can ask the question, where are the cached file, any file that you bring over, where are they stored? And the answer is, depending on the implementation, you can store the files that you brought over from the server either in disk or in memory. If you store it in memory, access is very, very fast, but it's volatile. So if the machine crashes, any updates you have made will go away. If you store it on disk, then you will not be as fast as you stored in memory, but any changes you made will survive a reboot. So you can actually send those changes over if your machine crashes and you reboot it. Yeah, but accesses are local, but they're still slower than if the cache was in memory. So that's basically what this is saying. The cache could be a local disk or local memory. And you will have your speed versus reliability or non-volatile nature of the storage coming into the picture here. So that's where you would put the cache. And then the last point with respect to caching is whether you do write through or write back. Yeah, remember a few lectures ago, I said whenever you have caching, you have to deal with whether it's write through cache or a write back cache. Okay? A write through cache is whenever you write to a cache, you also send the changes over to a server. Okay? Write back essentially says you make a local change, you send it to a server at some later point in time. Now, for performance reason, if you did write through, there's no real performance benefit of writes when you bring a copy over, because every time you do a local write to that copy, it's also sent to the server. So you will see the full latency of a remote write coming into the picture. So most implementations will use write back caching. Like NFS is a good example where you can make writes, and then it may every 30 seconds it is going to flush all dirty blocks. Any change writes that are made in the past 30 seconds are going to be flushed. So there's a 30-second latency before any changes made to a file on some client are actually seen by the server. Okay, so this obviously brings consistency problems, but is done for performance reasons. Okay, so this is the same performance versus consistency trade-offs. Okay. So I'm going to stop here today. There are a few more slides here which we will talk about next time. Okay, so I have the midterm exam here, so I can hand those out.